Here, Padmani Bhore from MIT Academy of Engineering. Today I am going to explain you the topic about a support vector machine and hyperplane and the types of the SVM. Support vector machine itself is the definition is one of the most popular and versatile supervised machine learning algorithm. It is used for the both classification and regression tasks, but in this thread we will talk about the classification task basically, and it is usually preferred for the medium and the small size data set. Now here you can see how that SVM is to need to find the optimal hyperplane which is linearly separable data points in the two component by maximize the margin. So suppose if you have the data set and we wanted to classify in the two classes green and pink, so that will be separated with the two colors in the two component with this margin, which is to be called as a hyperplane. So now here are some basics of linear algebra that will be used in the SVM. So vector here are the mathematical quantity which has both magnitude and the direction, and the point in the 2D plane can be represented here as a vector between the origin and the point. So here you can see which figure out here QA vector with some length between the O and E is its magnitude, and the length of vector are also called as the norms. It tell how far the vectors are from origin. So here you can use the length of vector for the multiple inputs like x1 x2 to dash dash dash, and we have used here three inputs x1 x2 x3, which is to be calculated with the vector square root of x1 square plus x2 square plus x3 square. So now here the directions of the vector can be written here and calculated as per this formula and the dot matrix formula. So dot matrix between the two vector is a scalar quantity. It tells how the vectors are related with each other. So here suppose we are using u and v are the two vector, and the dot product will be calculated here with the symbols. For the inner product is a dot, and this is nothing but your theta, that is angle between the u and v, which represented here with theta, and length of vector that is with that particular u and v, and that can be represented with this particular formula, and that is calculated with this x and y axis, that is x1 into x2 plus y1 into y2. So here again we can able to calculate the hyperplane. It's a plane that linearly divides the n-dimensional data point in the two component in case of 2D. So hyperplane is a line. In case of 3D, it's a plane. So this is the condition that when you are using two component, it's a hyperplane. And if there is a condition that in case of 3D, it is a plane. So it is also called as an n-dimensional line. So here you can see in this figure that a blue line, which is nothing but you can say that it's a hyperplane, and linearly, which is a linearly separate the data point in the two component. And figure 3 here sorry, here you can have figure 3, which is represent hyperplane, is a line divided the data point into the two classes, that is a red and green. So that is what a linearly separable and not a linearly separable. So suppose you wanted to represent with a plane and not non-separably part, so that can be represented with this. And if it is a linearly separable, you can represent with the two separate points separated by one of the margin or the line. So linearly separable here, the represented with some line equation you can have, that is y equal to a into x plus b, that is nothing but a into x plus b minus y is equal to 0. So this is a hyperplane, which is a line divides the data point into the two classes, which is written with this equation, and x is equal to x comma y, and w is equal to you can have a minus 1. Then in the vector form hyperplane, which is given with the weight with the input plus b is equal to 0. And here you can have this diagram that is with the linearly separable. So what if the data point is not linearly separable, and in that case it can be look like this, that can separate the data points with non-linearly in this given figure 4. So this type of situation come very often in the machine learning, which is raw data are always non-linear here. So if the data is not labeled or raw data, then in that case particularly that can be represented with this not linearly or non-linearly separable data. So it is, you can say, so is it a doable? Yes, we will one extra dimension to data point to make it separable. So process of making non-linearly separable data point to linearly separable data point, which is also to be known as a kernel tree, right? So whenever we will try to separate the no the raw data with the label data, then in that case we whatever the data point or logic or trick we are using, that is to be known as the kernel trick. So here using this kernel trick, that we can see the data points are still linearly separable in this case and can be represented with this. So here we can have the two types of the vector machine. One is the linear SVM and the simple SVM. So linear and simple SVM is for the linearly, that is the labeled data which we can see that can be easily separable with the margin or with the any kind of linear line. And non-linear, it means that the data set which is not labeled or raw data and cannot be able to separate with the linear line or any kind of margin, then in that case we can able to use some kind of trick logic to represent that particular data set either in the form of plane or in the form of some multiple using some two or three access points. So in that case we can call it as non-linear SVM or the kernel SVM. So optimal hyperplane, here we can have, there are the number of hyperplane that can be separate the data point in the two component, and so optimal hyperplane is one which divides the data points very well. So here we can see that how the data is going to be separated with this hyperplane, where the that labeled data can be separated, and we will try to fix the line, that which line is fit to separate this two sets, two data sets. Okay, so that is to be called as a optimal hyperplanes. So we can find out the perfect margin or the line which can separate these two data sets. Here, that how we are choose the optimal hyperplane. So here let's assume that the solid black line figure is optimal hyperplane and two dotted line is some hyperplane which is passing through the nearest data point to the optimal hyperplane, and then distance between the hyperplane and optimal hyperplane is known as a margin. So whenever we are separating the two data set, and we'll try to find out the distance of the this margin with the nearest data point of this one set and the other set, and we'll get this a line, this margin that makes a distance from this center margin, so that maximize its distance at which is to be called as a support vector. This is to be called as a support vector. So we are maximizing this particular margin in this case. Okay, and in so that we can able to choose the optimal hyperplane here using this support vector points. So once we selected that support vector points, in that case we'll try to find out the maximum margin with this hyperplane, and in SVM our goal is to choose the optimal hyperplane which is maximize our margin. Okay, so thank you for the today's video of this SVM, in which we learn about this types of SVM and hyperplane. Thank you.